Today's chapter is chapter 34, and we're gonna learn about surface treatments, coatings, and cleaning. And this is gonna be the last chapter that we will cover, and last chapter that will appear on your exam. So, surface properties of a part is also important in determining its performance during service. And we're gonna take a look at in this chapter some surface finishing operations that can be performed on parts for technical or aesthetic purposes. We're gonna cover the surface treatments, cleaning, and coating processes such as shot peening, laser peening, roller burnishing, which usually is done to enhance mechanical properties of the surface. We're gonna take a look at coating operations such as cladding, thermal spray operations, physical and chemical vapor deposition, electroplating, and some other techniques. So after the part is made, some of its surfaces may have to be processed further to ensure that they have certain specific properties and characteristics. So if we want to sum up all together, what is the reason we need surface treatments, we can say to achieve improvement against wear, erosion, or indentation for parts such as shafts, rolls, gears, or to reduce friction. And we know how friction adversely affects the manufacturing processes. So we can reduce friction on surfaces of tools, dies, bearings. If necessary, we can reduce adhesion. Adhesion is just tendency of surfaces to cling into each other. So, for example, we can reduce adhesion for electrical contacts and improve resistance to corrosion, oxidation. These are very important, especially for medical devices, food packaging, or gas turbine components. Improve fatigue resistance of bearings, shafts with fillets. Rebuild surfaces on worn tools, dies, mold, or machine components. Modify surfaces like their appearance, their dimensional accuracy, frictional characteristics, or just to impart decorative features like texture, color. So, to achieve these specific properties and characteristics, a variety of techniques can be employed for metallic, non-metallic, and ceramic materials. These mechanisms include plastic deformation of the workpiece surfaces, like inducing some compressive stresses, or chemical reactions, or thermal treatment, deposition, implantation, organic coatings, and paints. So all of these we're gonna see is used in a variety of different techniques, and each of these techniques we're gonna see one by one. Now we're gonna take a look at mechanical surface treatments. These are done to improve the mechanical properties of the surfaces of parts and components. And the first one is shot peening. The shot peening, it is also known as shot blasting. This is a cold work process used to finish metal parts to prevent fatigue, stress corrosion failures, and prolonged product life for the part. So what we have here, we have small spherical shot that bombards surface of the part to be finished. So this impact is done with cast steel, glass, or ceramic bowls. And these bowls, they dimple the surface, causing compression stresses under the dimple. This technique is applied to gears, shafts, turbine blades, connecting rods, engine blocks, compressor blades, springs, just to enhance the mechanical properties like increased fatigue resistance and corrosion cracking. So pretty much the lifetime of the part is prolonged with this technique. But you need to keep in mind that if we're gonna use this part at high temperatures, the stresses can relax and this can lose its effectiveness, this technique. With the same concept, the process can be done with lasers, so which is called laser shot pinion. It is basically again a cold work process in which the metal part is struck by a high energy pulsed laser beam producing high amplitude stress waves like we are seeing in the image. So the surface material resists to stretching induced by the stress waves, resulting in a formation of compression stressed skin. In this process, prior to laser peening, the material surface is coated with an opaque layer of a black paint, and the black layer is then covered with a transparent overlay like flowing water. So the material of the black layer has low heat of vaporization. So when the laser strikes the workpiece surface, the pulse energy is absorbed by the opaque material, which heats up, vaporizes, and forms a high temperature plasma. And the plasma gas is going to be trapped between the workpiece and the transparent water layer, limiting the thermal expansion of the gas. As a result, the gas pressure increases to an extremely high volume. So this high pressure is transmitted to the workpiece, producing a shock wave which travels through the part and generates compression stresses. It is just a cold work. There is no heating nor melting. And the purpose of the water, as I explained, is just to confine the high pressure plasma gas. It is not related to the cooling of the workpiece surface. So the depth of the residual compression layer produced by laser peening is 4 or 5 times deeper than the compressed zone produced by shot peening. So these compression stress regions, they inhibit the crack initiation and propagation. Therefore, they are increasing the fatigue strength. So for what type of materials this process can be used? It is for titanium, nickel alloys, steels, possible for aluminum alloys. They can all be treated with this technique to improve fatigue, stress corrosion cracking, corrosion fatigue. And the parts that can be employed like gas turbine engine fan blades, gears, discs, shafts. Water jet peening. In this case, instead of laser or balls, we use water jet. So the water jet impinges on the workpiece surface with the same principles we have learned, induce compressive residual stresses and achieve subsurface hardening that is at the same level as in shot peening. So this technique has been successfully used on steels and aluminum alloys. Roller burnishing, or also called surface rolling. The surface of the component is cold worked by the action of a hard and highly polished roller or set of rollers. This process is used on flat, cylindrical, or conical surfaces. It improves surface finish by removing scratches, tool marks, pits, and induces compressive surface residual stresses as well. So since it removes the pits, scratches, any type of corrosive product or residues cannot then trap in the surface, and this helps with the corrosion resistance. It improves the corrosion resistance of the part. So it is a chipless machining method. It is just a cold working without cutting or abrading the surface. It doesn't remove any material, but rather compresses, like irons out the peaks of a metal surface into the valleys. So it is both improving the mechanical properties and also improving the surface finish. So we are seeing different burnishing tools, and you are seeing rollers are rotating and just achieving a finishing of metal surfaces without removing any material. It can be used in conical surface or a flat surface to improve fatigue life. So next is mechanical plating and cladding. So let's start with mechanical plating. It is other names like mechanical coating, impact plating, or pin plating. And in this case we have fine metal particles. They are compacted over workpiece surfaces by using glass, ceramic, or porcelain beads. Propelled by rotary means such as tumbling. In this image you are seeing those beads and the part that has been coated. So metal particles together with these beads put in the tumbler. If you watch the videos you can see, and then basically with cold welding the metal particles are welded onto the surface of the part. This technique is commonly used for nails, screws, nuts, springs. common coating materials are zinc, tin, copper, and aluminum. So cladding or clad bonding, we have seen this technique before. Here the parts are bonded with a thin layer of corrosion-resistant metal through the application of pressure by rolls or other means. There is possibility it could be explosives can be used, extrusion, but in this case the idea is the same. Usually this is to achieve corrosion resistance, where we provide a surface layer. It can also improve wear resistance, electrical conductivity, thermal conductivity, or improve surface appearance. This is mostly can be used to form like composite materials. We can give cladding of aluminum as an example. Here surface layers of weaker but more corrosion resistant single phase aluminum alloys are applied to a base of high strength but less corrosion resistant but age hardenable stronger material aluminum alloys core. Stainless steel can also be used to clad steels, reducing the need for nickel and chromium alloy additions throughout. Thermal spraying is a process in which coatings of various metals, alloys, carbides, ceramics, and polymers are deposited on metal surface by a spray gun with a stream heated by an oxy-fuel flame or an electric arc or a plasma arc. The surfaces to be sprayed are first cleaned of oil and dirt, then roughened by some maybe grit blasting to improve bond strength between the surface and sprayed metal or material. So the coating material can be in the shape of wire, rod, or powder. When the droplets or particles of this coating material impact the workpiece, they solidify and bond to the surface. So temperatures can range in from 3000 degrees C to 8000 degrees C. This sprayed coating is hard and wear resistant, but this is a spraying procedure, right? So there will be air trapped or oxide particles trapped. So this coating layer is actually have a porosity as high as 20%. Typical applications of thermal spraying include engine components and storage tanks, rocket motor nozzles, components that require resistance to wear and corrosion, crankshafts, nozzles, engine blocks in an automobile, and so many other parts where you require resistance to wear and corrosion. And thermal spraying is also used for just painting the surfaces, so for aesthetic purposes also can be used. So in this figure we are seeing illustrations of thermal spray operations. The first one is thermal wire spray. In here the oxy-fuel flame melts the wire and deposits it on the surface. You see the workpiece and you see the fuel gas and oxygen coming in together with the wire or rod of the metal that you want to do the coating of, and then it sprays it on top of your workpiece, and then it is deposited as a coating on your workpiece. And the bond is of medium strength and the process is relatively inexpensive. So I should also say bond strength depends on the particular process and the techniques being used. And image B, we are seeing the similar process this time, but the name is thermal metal powder spraying, and as the name implies, instead of wire this time we have metal powder added to the process. Instead of the wire we have metal powder, and again it is molten with the flame, the same type of flame, and then it is sprayed on the workpiece and deposited as a coating. And there is plasma spray. So in this case the source of energy is not combustion like within a flame, but it's electrical. Okay, the first two was combustion spraying, and this one is electrical spraying. In this case we have plasma. So a high energy or vacuum plasma produces temperatures on the order of 8,300 degrees C and results in good bond strength with very low oxide content, as well as very low levels of porosity. Okay, so there are now vapor deposition techniques. In these processes, there are different types of vapor deposition processes, and in these processes there's gonna be a workpiece, and workpiece will be called the substrate, and this substrate surface is subjected to chemical reactions by gases containing chemical compounds of the material to be deposited. So in the gas phase, this gas phase is in contact with your workpiece, and the gas phase contains whatever the material you want to deposit. And coating thicknesses can be very thin in this process, like because you do deposition atomic layer by layer, you can control it. So the coating thickness is usually a few microns, and it will depend on the technique, processing parameter you are employing, etc., because there are a lot of processing parameters that you can play with to change, control the composition, thickness, porosity, and everything. The substrate can be a metal, it can be a plastic, glass, or paper. And what type of materials you can deposit is metals, alloys, carbides, nitrides, borides, ceramics, and oxides. So a lot of possibility. And typical applications here are these processes are used for like cutting tools, drills, reamers, punches, dies, wear surfaces, milling cutters. There are two major vapor deposition processes. One is physical vapor deposition, PVD, and other is chemical vapor deposition, CVD. Let's learn about physical vapor deposition first. Okay, there are three basic types of physical vapor deposition processes: vacuum deposition, sputtering, and ion plating. These processes are performed in a high vacuum and at temperatures in the range of 200 to 500 degrees C. So remember, you are doing deposition from a vapor phase, right? You don't want any type of impurity, any other form of particles floating in the air. You cannot do a good deposition, you cannot get a good quality film. That's why these processes always require high vacuum. So the particles to be deposited are carried physically to the workpiece. But in chemical vapor deposition, it will be chemical reactions that are carrying the deposited particles that are going to be deposited onto the surface. So the first type is vacuum deposition. In the vacuum deposition or evaporation, the metal is evaporated at high temperature in a vacuum and is deposited on the substrate, usually at room temperature or slightly higher for improved bonding. So in this technique, the coating material, which is also we called cathode, you are seeing, is evaporated by several evaporators, like this one, that one, this one here. So this evaporation happens using highly localized electric arcs, and the arcs produce a highly reactive plasma. Plasma is gonna be consisting of ionized vapor of the coating material, and then the material condenses on the substrate, and the substrate you are seeing in the middle, it is the anode, and it is gonna coat the substrate. These applications can be functional and decorative, like functional means maybe oxidation resistant coatings for high temperature applications, electronics or optics, or just aesthetic purposes. Next is sputtering process. In this process, an electric field ionizes an inert gas, usually an argon. You can see the power supply that is attached between a cathode and anode. This provides the electric field, and inside there is the inert gas. In this case, this is argon, for example. So what happens is this gas is ionized, and the positive ions then bombard the coating material, which is at the cathode. You see as the target as blue color. So this causing the sputtering or ejection of its atoms. So you have the coating material, it is ejecting its atoms. Those atoms then go condense on the workpiece, which is heated to improve bonding. Another technique is ion plating. This is like a combination of sputtering and vacuum evaporation. Basically, there is an electric field, as you can see, applied that causes a glow, meaning generating a plasma, and the vaporized atoms are ionized only partially. So here we have bombarding species along with depositing particles, and I see an evaporator filament. That means just like in the vacuum deposition, there is an evaporation going on of the particles that we are trying to deposit, and also the bombarding particles. So these come from like it is in the sputtering from the inert gas. Here the bombardment prior to deposition is used to clean the substrate surface. during deposition, the bombardment is used to modify and control the properties of the depositing film. So as we said, it is basically a combination of sputtering and vacuum evaporation. Okay, so what is chemical vapor deposition? So chemical vapor deposition is an atmosphere controlled process carried out at temperatures in the range of 950 to 1050 degrees Celsius. In this case, cleaned tools ready to be coated are staged on a pre-coated graphite work trays or shelves and loaded onto a central gas distribution column. We call it tree. The tree, loaded with parts to be coated, is placed inside the CVD reactor. The tools are heated under an inert atmosphere until the coating temperature is reached. So typically, we use this technique for coating of cutting tools with titanium nitride. So that's why we are going to give an example based on that in order to understand the process. So this is going to happen again as we talked in an inert atmosphere. So we have titanium tetrachloride as a gas, hydrogen and nitrogen as a gas, which are introduced into the chamber. So remember, we need the coating in the gas phase first. So the chemical reactions will take place between those things we introduced into the chemicals we introduced into the chamber. So the chemical reactions deposit titanium nitride on the tool surface with the hydrogen chloride that is produced exhausted from the reaction chamber. So here we're seeing the pre-coated graphite work trays. You are seeing here graphite shelves as labeled, and then loaded onto a central gas distribution column. We called it a tree, and you can see that too. Here you can see where the carrier gases are getting in and where the exhaust gases are getting out, and you see the tools to be coated put there. The tools are heated under an inert atmosphere until the coating temperature is reached, and the coating cycle is initiated by the introduction of titanium tetrachloride, you can see here, together with the carrier gases like hydrogen and methane onto the reactor. So here the titanium chloride, it's a vapor and transported into the reactor via the hydrogen carrier gas, and then there is the methane. So there is gonna be certain reactions going on, okay? So there will be chemical reactions that are forming the titanium nitride at the end. So first what's happening here is you introduce this gas, reacted with methane, which formed titanium carbide and hydrogen chloride. So after that, and what happens, we have a nitrogen and hydrogen gas mixture is also introduced that is going to react So depending on what you want to synthesize, right? Do you want the form titanium carbide, or do you want to form titanium nitride? So it will depend on, then you should change your gases. If you substitute methane with nitrogen and hydrogen gas mixture, then you end up with getting titanium nitride, and you can get titanium carbide through this technique also. So at the end, it will depend on what type of carrier gas you are introducing into the system. The chemical reaction taking at the substrate surface, and then usually that's why they put some catalyst materials sometimes at the substrate surface to activate the reactions, these chemical reactions on the surface of the substrate. And then you need to be careful, because there might be toxic exhaust gases that are released. In this case, it is hydrogen chloride, so we don't want to be exposed to that, right? It is toxic. So in general, CVD coatings are thicker than PVD, and it is a long process. It might take like hours of heating, coating, and waiting for it to cool to room temperature. But a lot of parameters you can control: the thickness of the coating with the temperature, time, or flow rates of the gases that are being used. Almost any material can be coated. Any material can serve as a substrate, but that doesn't mean there will be a good bonding strength. So not all substrates will bond very strongly to the not all coatings will be bond strongly to the substrate. This process is also used to produce diamond coatings on top of substrates. So let's talk about electroplating, electroless plating, and electroforming. So plating imparts resistance to wear, resistance to corrosion, high electrical conductivity, better appearance, and reflectivity. So either you want to enhance the properties or just aesthetic purposes, you do plating. So the first one is electroplating. In this one, you have a workpiece as cathode that is plated with a different metal, which is going to be your anode metal. This is transferred through a water-based electrolyte solution. If you take a look at the image here, the illustration of the electroplating process, you see you have your part to be plated, that is the cathode right there. And we want to coat this with a copper, and copper is going to be the anode, which is going to dissolve into the solution. You see the copper ions, which are then reduced on the surface of the cathode, meaning the copper ions will become copper and deposited on top of your part's surface. This way you are coating the surface. For this to happen, you need to have electrolytic solution, meaning this solution needs to carry the ions. So there are a lot of different chemical reactions might be taking place here. And metal ions from anode are discharged by means of electric potential energy from an external source of electricity, or are delivered in the form of metal salts. That is also possible. Metal ions are dissolved into the solution and are deposited over the cathode, as I explained. So we are also seeing some examples of electroplated parts right there. Workpieces with complex shapes may require a modified geometry because of varying plating thicknesses, and this can be seen here in this image right there. So in electroplated parts, there can be non-uniform coatings, like you are seeing, due to complexity of the shapes, like the corners, which you need to be careful about when doing electroplating if you want to achieve a uniform plating thickness overall. And you see the sharp corners in this image, that will result in poor electroplating, meaning non-uniform thicknesses overall. But if you don't have sharp corners, or when you have rounded corners like this, the quality in this type of shapes will be good, okay? Good quality in terms of electroplating, meaning good quality, meaning uniform plating thickness overall. With this technique, you can say that channels, crevices, or slots are difficult to reach in coat with the anode material. Before we go to electroless plating, examples of electroplating, like common plating metals are chromium, nickel for corrosion protection, cadmium, copper for corrosion resistance and electrical conductivity, tin, zinc, especially zinc is for corrosion protection for steel. Metals such as gold, silver, platinum, these are important electroplating materials in the electronics and jewelry industry for electrical contact or decorative purposes. And plastics like polypropylene, polycarbonate, they also can be electroplated. But you need to be careful because the plastics are not conductive. Therefore, first they need to be prepared with a type of plating needs to be formed, which is conductive first. So they are coated with electroless nickel plating first before doing the actual electroplating process. Okay, and then there is electroless plating. This process is carried out by a chemical reaction without using an external energy source of electricity. And the most common application is using nickel as the plating material. Copper is also being used. So in this case, we have nickel chloride, which is a metallic salt, which is reduced with sodium hypophosphite as a reducing agent to nickel metal, which is then deposited on the part. So instead of electricity supplying the electrons and reducing the ion, for example, copper, making copper ion to copper, in this case we just have a reducing agent in the solution named sodium hypophosphite. So this reducing agent is turning the nickel ions into nickel, and this is being deposited on the surface without the use of electricity. And this coating has excellent wear and corrosion resistance. And unlike electroplating, cavities and inner surfaces of tubes can be plated successfully. And this can also be used for non-conductive materials, like we have talked about, ceramics and plastics. This is expensive, more expensive than electroplating. But unlike electroplating, the coating here is the coating thickness of electroless plating is always uniform. So that's the advantage. What is electroforming? So the name implies forming, right? This is the formation process, fabricating process. Here there is a mandrel, and metal is electrodeposited on the mandrel, which is then, the mandrel is then removed, but the coating itself becomes the product. So you are forming something. Both simple and complex shapes can be made by electroforming. And you are seeing here typical sequence in electroforming. There is a mandrel selected with the correct size. and there is the desired geometry is machined into the mandrel in second stage, and then the desired metal is electroplated with the blue coating you are seeing on the mandrel. So this includes electroplating first, and then the plated material is trimmed if necessary. Let's say you want a certain shape, you can trim it, and then the mandrel is dissolved with some chemical machining, and then you obtain the part. So here we see examples of parts that are formed with electroforming. So basically this is a fabrication process. So before we go to anodizing, we can say mandrels, they are made of a variety of materials, including metals like zinc, aluminum, non-metals, low melting alloys, wax, plastic. So these are melted away or dissolved with suitable chemicals. So what is anodizing? Okay, so anodizing is basically intentionally oxidation process. If you want to form oxide layer on top of a part due to reasons, because we have learned that each oxide layer has its own characteristics, right? Chromium oxide provides against corrosion, or formation of aluminum oxide is again preventing corrosion of aluminum, but it is also a porous layer. If you watch the videos, you can see those aluminum oxide layers are used for coloring our iPads, iPhones. So sometimes we want intentional formation of an oxide layer on top of our part. Again, this can be due to you want to color it, for example, with dye. Anyhow, there are different types of purposes that you can achieve with the formation of an oxide layer. And in this case, it is simple. We have an anode and a cathode, and basically this is like an electrochemical process, but the reverse of electroplating. So the workpiece is the anode, or in the electrolytic cell. And so this anodizing is accomplished by just immersing this aluminum into the acid electrolyte bath. You see sulfuric acid electrolyte, and we are passing an electric current through the medium, and a cathode is mounted to the inside of the anodizing tank, and aluminum acts as an anode here, as I said, so that the oxygen ions are released from the electrolyte to combine with the aluminum atoms at the surface of the part being anodized. So therefore we can actually, normally aluminum can form its own oxide layer, we know that, but then this process can control the oxidation and control the thickness of that oxide layer. Hot dip coatings. Large quantities of metal products are given corrosion resistant coatings by direct immersion into a bath of molten metal. The most common coating materials are zinc, tin, and aluminum. There are also lead alloys, but it has been discontinued. So hot dip galvanizing is the most commonly used method for imparting corrosion resistance to steel. So remember, galvanizing means coating the steel with zinc. So first you clean the products, remove all oil, grease, scale, rust, and then dip them into a solution of zinc ammonium chloride and then dry. Next, It is immersed in a molten metal bath of molten zinc, and then zinc and iron react metallurgically to produce a coating that consists of a series of zinc and iron compounds and a surface layer of pure zinc. Remember zinc, if you learned about corrosion in your educational life, zinc here acts as a sacrificial anode to the iron, and it dissolves, it corrodes itself, protecting the iron. So this is an example to galvanizing, hot dip galvanizing process. Well, a typical continuous hot dip galvanizing line for sheet steel is shown in the figure. The rolled sheet is first cleaned, then scrubbed by brushing. The sheet is then annealed in a continuous furnace with controlled atmosphere and temperature and dipped into a molten zinc at about 450, and the thickness of the coating can be controlled by whipping action from a stream of air or steam, and we are seeing the flow line for this process here. And paints, they are classified as they are for decoration, and they are classified as enamels, lacquers, and water-based paints. So they are by far the most widely used finishes on manufactured products, and a great variety is available to meet the wide range of product requirements. Most of today's commercial paints are synthetic compounds that contains pigments, and water is the most common carrying vehicle for the pigments. And paints are available with good resistance to abrasion, high temperatures, and fading. Common methods for applying paint are dipping, brushing, rolling, spraying. So in this case, enamels, these are producing a smooth coat with a glossy or semi-glossy appearance. Lacquers, these forming an adherent film by evaporation of a solvent, and water-based paints applied easily but can have a porous surface and absorb water, making them difficult to clean. So as we talked about, there are different ways to apply paints. We see here in dip coating, obviously the parts are dipped into the tank which has the paint, and and the flow coating is, as you can see in image B, involves spraying of a component with excessive amounts of paint or applying streams of the coating material to it. The excessive coating will drip off, then it's collected, filtered, and reintroduced into the system again. And there is the electrostatic spraying. The paint particles are charged electrostatically and they are attracted to the surfaces, producing a uniform coating. So we have talked many times how it is important, especially during the joining processes or any other type of sorting treatment. The cleanliness of the surface is very important if you want to achieve strong bonding between the surfaces and the coating to the substrate. Then how do we define the degree of cleanliness or clean for a surface? So there can be two simple tests that can be done. One is water break test, just observing whether water is going to uniformly coat the surface. If water collects as individual droplets, then it means the surface is not clean. And there is also another way of wiping the surface with a clean coat to see if there are any residues on a white cloth. A clean surface can have both beneficial and detrimental effects. Although a surface that is not clean may reduce the tendency for adhesion in sliding, thus reducing friction, cleanliness is necessary. We know for applications such as coatings, paints, adhesive bonding, brazing, soldering, welding operations. So also the type of cleaning process will depend on what type of metalworking fluid you have or contaminants you need to remove. In water-based fluids, for example, are easier and less expensive to remove than oil-based fluids. Contaminants, also called soils, may consist of rust, scale, chips, various metallic, non-metallic debris, lubricants, pigments, polishing compounds, and general environmental elements. So how do we clean up these parts then? So there are three techniques, or we should say three ways to do it, like mechanical cleaning, just physically removing the contaminants with a wire or fiber brushing, or abrasive blasting, tumbling, or with water jets, or some ultrasonic cleaning, which is effective to remove rust, scale, or other contaminants in the surface. Or there is electrolytic cleaning. The charge is applied to the part to be cleaned in a solution. The charge develops bubbles of hydrogen and oxygen, and then these bubbles are abrasive, and then they help remove contaminants from the surface. There is also chemical cleaning, as the name implies. In this case, chemicals are being used. Usually this is for removing oil or grease from the surfaces, which is difficult to remove. So there are a variety of different chemical cleaning techniques are available. If which you are interested, you can check your book. So the summary here is we learned about surface treatment processes, and we have learned that the purpose might be different behind the surface treatment. It can be to increase mechanical, chemical, or physical properties, or it can be just providing corrosion resistance, wear resistance, or friction fatigue resistance. The processes include metalworking, heat treatment, deposition, plating, and we talked about the cleaning of the surfaces, and it is important in many of the manufacturing process to achieve a clean surface, and how this clean surface can be achieved with different techniques.